Greetings to one and all. I am Harshada Mali, a junior research fellow working at Department of Audiology, All India Institute of Speech and Hearing, Mysore. Here I will be sharing our results from our work profiling individual differences in vertical localization, insights from three virtual test paradigms. Sound source localization in the vertical plane contributes to a complete three-dimensional auditory scene. This means that we don't just localize sounds to our left and right, we also perceive whether the sound comes from above, below, front, or behind. However, vertical localization, especially under virtual, that is headphone-based conditions, has been relatively less explored. Emerging studies motivate and remind us that vertical sound source localization also deserves deeper research to strengthen our understanding of how individuals identify sounds that are vertically oriented in space. We included 35 young adults with clinically normal hearing, evaluated using the standard pure tone audiometry, tympanometry, and reflexometry. All the participants were screened for normal cognitive functioning by administering NEST, and they were screened for auditory processing disorders using the SCAP-A tool. Three virtual test paradigms were developed to assess vertical localization in the median sagittal plane. The first one was a front-back plane identification task wherein the participant was expected to report whether the incoming sound was perceived in the front plane or the back plane. The second paradigm was used to assess the top-bottom plane identification accuracy, and the third one was a vertical discrimination task wherein two vertically spaced stimuli were presented as a pair and the participant would report whether he perceived it to be similar or different. A 1000 millisecond wideband noise was convolved with non-individualized HRTFs for the given elevations using MATLAB and SLAB 3D softwares. These are the plotted spectral envelopes of auditory spatial stimuli used in all the three paradigms. For stimulus presentation and response recording, a custom written MATLAB code with a graphical user interface was used. Each paradigm consisted of three phases, the first one being the stimulus familiarization, wherein the participant would click on locations on the GUI to listen to the stimulus and to understand its spatial layout. A task familiarization included presenting 10 trials with corrective feedback. And the test phase finally would consist presenting 10 trials for each plane in both the identification paradigms and 5 trials for each non-identical pair in the discrimination paradigm. Now coming to how the scoring was done for each paradigm. In the front-back identification paradigm, only the stimuli that belong to the front or the back were scored. As you can see, this 90-degree elevation, it does not belong to any front or back planes, hence it was not scored. Similarly, for the top bottom, the 0-degree elevation was not scored. This comes to a score of 20 per plane and 40 per identification paradigm. Under the discrimination paradigm, 5 catch trials included presenting identical pairs. These pairs were not scored, wherein 5 test trials that included non-identical pairs were scored. This comes to a total score of 210 for the discrimination paradigm. All these scores were subjected to Shapiro-Wilk test for normality. Post-conversion to Z-scores, hierarchical cluster analysis was run to group individuals with similar profiles. To validate this clustering, Fisher discriminant analysis was done to assess the error in classification. Data was normally distributed. As we can see in the dendrogram, 3 clusters were identified. The first cluster did good in the top bottom identification paradigm. The second cluster performed good across all the paradigms, and the third performed poor at all the paradigms. The discrimination of good and poor was based on the total mean obtained across all these paradigms. The Fisher's discriminant functional analysis yielded two equations, one of which was heavily loaded on the top-bottom accuracy scores and the other was loaded on front-back accuracy scores with equal weightage to discrimination accuracy scores across both these equations. The overall accuracy of classification was 97.1%. Only one participant from cluster 1 was misclassified to be present in cluster 2 as all the scores were near the mean of the cluster 2. The results show that spatial abilities vary independently within individuals, even those with clinically normal hearing when it comes to vertical localization. Why such variability is because as vertical localization heavily relies on spectral cues shaped by the outer ear, particularly pinna. This varies person to person. And also how an individual uses or weighs these cues and whether the generalized HRTFs match their unique morphology could underlie the variability in the performance. So in real world environments, people with vertical spatial deficits may struggle to localize sounds in the median sagittal plane. One limitation is that we use generalized HRTFs and not individualized ones. So although these paradigms are effective, the stimuli are effective, but it may not truly capture each listener's ability to use the spatial cues. A larger sample would definitely help to confirm the stability of these cluster patterns. Future research should investigate whether these profiles are stable over time and if targeted training can improve performance in specific spatial dimensions. From this study, we can conclude that there are distinct profiles that exist when it comes to front, back, and top, bottom plane identification as far as vertical localization is concerned. So spatial processing is definitely not uniform across listeners. Also, it is not uniform across the dimension that is being tested. There is a need to adopt a multidimensional framework when we are assessing spatial hearing abilities. The study has also provided a few normative benchmarks, and it also fuels a need to develop targeted auditory training interventions. Thank you.